Welcome to CS3510. This is a little extra thing on lower bounds. So lower bounds in the context of the algorithms we've done specifically for sorting and for binary search, and in general. First off, what is a lower bound, right? We have in big O we say f of n is O of g of n if there exists constants c and n naught such that f of n is less than or equal to c g of n for all n greater than n naught. So eventually some constant multiplied by g will overtake f. So as a picture you can think of this as f or something, right? And then this is g. This is O of f, right? Something that upper bounds it, and then this is just f, right? So a big O is like an upper bound. It tells you a maximum of the function. And to find, let's say you fix some problem, to find a big O of that problem, all you have to do is give an algorithm. So there's two perspectives. First off, take a algorithm, what's its runtime? That's big O of some problem. Every algorithm solves some problem. Go the other way. Think about the relationship not from algorithms to problems, but problems to algorithms. Fix an algorithm and consider all possible, fix a problem, for example, sorting. Consider every possible algorithm that solves sorting. That's what a lower bound is. We say f of n is omega of g of n if, again, there exists constant c and n naught. And this is an informal definition. There's a more precise one, such that f of n exceeds g of n, c times g of n for all n greater than n naught, right? So in some sense, down here is the omega of f, right? So algorithms, every algorithm is an upper bound on some problem. But say if you're considering a problem, how do you consider a lower bound? Getting a big O is easy, which is why we do it all the time. Just show, let's say you fix a problem like sorting. We gave merge sort in n log n time. That means sorting, an upper bound on sorting is n log n. Now if you have n squared or n cubed runtime for sorting through other algorithms, you can just ignore those because you know you have a better one, n log n. Now, how do you show a lower bound? This is much more difficult. You have to show for every possible algorithm, all of them must take some minimum number of steps. That is much more difficult. And I'll tell you in practice, the theoretical computer science community, basically we can't do this. So this we can do all the time. We do it a lot. There's 10,000 algorithms, okay? How many lower bound arguments are there? Probably less than 20. How many of them are accessible to an undergraduate? Like 3. So the ones that we have should be celebrated, and that's basically what the point of today's lecture is. Like every lower bound argument you should know in as an undergraduate student is the few ones that we do have. And there's big relationships to like the P versus NP problem. As a community, we failed to even prove some problems take n to the 0.001. We can't even prove something like that. You know, we can't do it. So many difficulties in this area just by the nature of what you're working with. But that doesn't mean we can't do it in general. So the first thing we'll prove, and we kind of already did when we talked about the lower bound for addition, which is that, actually before we get into the 3 results for today, any questions on this? Questions on lower bounds in general? Okay. The first one is almost every algorithm has a linear time lower bound. Why? It's got to read the whole input. That's basically it. Think about 2 ways we can do this quickly is addition. When we're adding bits, we mentioned that we gave a linear time algorithm for addition. So that was a linear time upper bound. And in the where n is the number of bits. And then we also mentioned that there's a linear time lower bound. Just to quickly rehash what that proof is, when you have a matching upper and lower bound, you've basically solved the problem because that gives you a theta. You cannot do it faster or slower asymptotically, right? the proof basically went the same way you would do it for any other proof with a linear time lower bound, which is that basically you have to read the entire input. So what you do is assume to the contrary it didn't read the whole input. So let's say we were adding these two numbers. Right? So assume to the contrary it could take only n minus 1 steps. Another difficulty in lower bounds is that in upper bounds you can kind of be vague about what a step is, because you're like, obviously 2 for loops, that's n squared. But then to precisely what is a step, what doesn't count as a step, can be subjective and maybe even architecture dependent. Does shifting take constant time or linear time? Does insertion into an array take linear time if you have to move all the memory over? Linked list versus array list, that kind of stuff can matter. Anyway, assume that it takes n minus 1 steps to add 2 numbers. Then some bit is not read. Repeat the execution of the algorithm, changing whatever that bit happened to be. So the answer will change, but the computer's steps will not. So on 2 different inputs, it'll output the same answer. So any algorithm that takes n minus 1 steps is then wrong. Contradiction. No such algorithm can take less than n steps to do addition. Now, this same argument would work for sorting. If you have n elements, suppose you have to take n minus 1 steps. One element is not read. So change that element to be a billion. Certainly the array, it'll still output the same answer, but it shouldn't, because changing that element will change what the actual answer is. Same thing for basically every algorithm we've done, right? The only algorithm that is an exception to this would happen to be which one? Binary search is the only algorithm we know of that beats that this is false for. It's the only algorithm that you should know, and variants of binary search, of course, that can beat a linear time lower bound. And again, one of the reasons binary search works is because it's promised to take, it's promised that the input is sorted. If it doesn't have that promise, then it doesn't work fast at all. If it has to verify the input is sorted, that takes at least linear. If it has to sort first, that takes at least n log n in the comparison model. So the fact that it's promised this is the only thing that allows it to speed up, right? Questions on this kind of argument? Okay. We mentioned that binary search takes O of log n time. What do you think a lower bound on binary search is? Yeah, in fact, there's a matching lower bound on binary search. It is the case that, like, you could think about, I don't know, best case, worst case, average case stuff for binary search. Can you always, is there, and again, not binary search specifically, because binary search is one algorithm, but the problem of searching. Given an array A and a target T, find I such that A of I is equal to T with A sorted. So that's the problem of sorting. So we look at the problem and we say, oh, binary search solves that problem in log n time. Now consider all possible other algorithms, anything creative that could solve that problem asymptotically faster. I claim none of them can solve it faster than binary search, and up to constants, binary search is in fact faster, the fastest algorithm, right? Now we're working in the comparison model. The comparison model is basically there's all kinds of other stuff you can do. But because of the difficulty of this for all part, where you're like, for every possible algorithm, each must take a minimum number of steps, there's many complicated and crazy things you can do with code. You guys know this. You can do all kinds of math. There's insane tricks. But in the comparison model, we say we mostly compare elements by a operation, and then we can make a decision based on that, right? So there's two things we can do we make one assumption about what the algorithm can do, which is that it must make a certain number of comparisons. And we assume that this operation has two distinct properties. First off is transitivity. A is less than or equal to B, and B is less than or equal to C implies that A is less than or equal to C, and that if one of these is true, when we're talking about binary searching over numbers or binary searching or sorting an array, of course these are true because the options are numbers. But suppose they contained objects that were not directly comparable, maybe functions or graphs or all kinds of other stuff, right? So that's why we always deal with numbers, is to assume that those properties are true. Now, in terms of the master theorem, do you recall what the recurrence was for binary search?
T of n over 2.
Yes. In some sense, the way binary search works is it makes comparisons, and for each comparison it makes, it's allowed to split the array in half. By the way, what's a worst case input for binary search? When do you go all the way down to the bottom?
When the element you're looking for is like, I don't know how to say it, not of power of 2 in the array.
Yeah.
Inverse power of 2 of n in the array.
That's a little more technical. What I could say is, and you probably also knew this, but it's like if the element actually isn't in the array, you'll bottom out searching for it, right?
Oh, right.
Yeah. So, but it's the same thing, right? As long as you go all the way down, quote unquote. But what do we mean by down? So what we can say is we may arrange all the possible answers into a binary tree. And every time we make a comparison, in any kind of comparison algorithm, we do it in such a nice way to make the tree even out, right? So every time you make a comparison, you can think about it as if you're splitting the tree in half, right? But the cool thing about binary search is that it specifically partitions it in an even sense, right? So consider every possible way you could arrange a tree. What is the least, the maximum depth over all trees, the least of those? It's going to be just exactly the answer for binary search. It's going to be log of n, right? And then we have our answers, right? But it doesn't actually take, the number of comparisons it must make is the depth. Right? So how many leaves are here in this tree, by the way? Let's say these are the leaves of such a decision tree are going to be the elements of the array, right? Oops. So as you go search through the tree, binary search has a nice property where it splits the array in half each time. And as it goes down, this tree, over all possible ways you could organize such a tree, the maximum depth of a tree is the number of comparisons that that algorithm makes, right? So you take the minimum over all of those, and you see that binary search actually reaches the optimal. If there's n leaves in a tree, what's the depth of the tree?
Log n.
Yes. So not only is it log n, but over all possible trees, the shortest depth, the shortest max depth of any tree is going to be log of n as well, no matter what it is, right? Now, it could be the case, for example, you have something like this, right? Let's say it's not a nice power of 2. It doesn't even out. But it's going to still have up to the next power of 2 log of that, which is still going to be log of n, right? So we see that binary search must make log of n comparisons. And again, this is in the comparison model, right? Kind of maybe a little obvious in some sense. Every time you make a comparison, you half it. And you can't do better than that asymptotically, right? Questions on that? Okay, let's talk about the sorting lower bound, right? So again, we're working in the comparison model. Sorting is the problem where you have an array unsorted of comparable elements, and then you output the sorted array, right? So we want to prove that sorting requires, in the comparison, at least n log n comparisons. Okay. So basically, if we can prove this, this will prove merge sort is optimal, average case quick sort is optimal, and things like this, right? So in some sense, sorting is a solved problem. Now, we'll talk about what does it mean if you're not in the comparison model, but we make the assumption of the comparison model simply so things are simple, right? It's true, you probably have heard of a linear time sorting algorithm, at least one, right? It's complicated. The comparison model, it's just nicer to work in. Everything works out. You work with multiple variables when you're doing in like radix and things like this, right? So the first question is, how many inputs are there?
N.
Yes, there are n elements in the array. How many possible outputs are there?
N factorial.
Yeah. Consider, actually, the other way around. You have, let's suppose the elements are not distinct. There's one output. So I said it backwards, sorry. There's one output. There's, which is the array 1 to n, right? But there are how many inputs? N factorial. There are n factorial possible inputs to an algorithm, right? Let's say you have a sorting algorithm that sorts an array of size n. The number of possible inputs to the array is going to be, the number of possible inputs to our sorting algorithm is going to be n factorial. But why? Yeah.
It's n factorial because they're just n elements and they can be arranged in any number of ways. So like, let's say we're just working with like 1 through 5, right? There are n possible elements at the first spot, then there are n minus 1 possible elements, then n minus 2, so forth until we.
Exactly.
Sorry, I don't think it's n factorial because you can repeat elements.
Suppose distinctness for easiness. If you can, and in fact, I'll comment about like when does this apply, when does this not apply. Let's just assume distinctness. Would you assume if it's not distinct, it's easier?
I suppose so.
Yeah, similar enough, I suppose. So there are n factorial elements because for the first item you have n choices, for the second item you have n minus 1 choices, and so on, and for the last item you'll be remaining with 1 choice. So there's n, just product those together, 2050 level combo, you are left with n factorial possible inputs. Okay. Now, consider that each time you have n factorial possible answers, and a sorting algorithm in a comparison model uses comparisons to reduce this n factorial set down to a single final answer, right? It has to make a decision about what is the final answer. It's the correct permutation in the right order. So it has to make a sequence of comparisons of the form like AI less than AJ. And it repeatedly does comparisons like this to shrink the answer set. So what we can say is that we may arrange the same way we did with binary search, where we arrange the n elements as leaves of a tree. We may not arrange the n elements as leaves of a tree, but the n factorial possible answers, right? So each of these could be leaves of a tree. And unlike binary search, where we get to assume that searching always splits it in half nicely and everything is good, sometimes you make bad comparisons. So it's possible to get binary trees that look like this. Okay? You could have a really long, bad tree. You could also have a really good tree, where each of the intermediary nodes is a comparison, right? Does anyone remember what these kind of binary trees are called? Balanced. Yeah, I think there's another word for it. Full? Yeah. I've also heard the word complete. Yes. So consider all possible binary trees, right? Where you have n factorial amount of leaves. Then we may say the number of comparisons of an execution of the algorithm on a specific input is the max depth of such a tree. Why? If you consider a tree like this, there might be a single input it finishes in constant time. For example, append every search algorithm, every sorting algorithm with a linear time check that just checks that the input is sorted, and then if it is sorted, just you're done. That could take n comparisons, so that branch might not be really deep, but it would be not super shallow. But then the actual runtime may be kind of complicated. So the worst case, and of course we're doing worst case analysis here, so the worst case would be the maximum depth, right? So what is the maximum depth, what is the minimum of the maximums? And this is the min over all trees, the maximum depth.
Log n factorial.
Yeah. Basically, the time, when is this depth going to be the least? Is if the tree is as full and balanced as possible, right? So if the tree looks like this, the depth is good, the max depth is going to be the least. If the more unbalanced the tree is, the longer the max depth. So the least max depth, the minimum max depth, is when the tree is as full as possible, right? So the depth of the tree, the number of comparisons, must exceed log base 2, in fact, let's say, of n factorial. Okay, and again, this is in the comparison model where the runtime is quite literally just the number of comparisons. We're almost done here. There's two ways we could solve this problem. First off, anyone know Stirling's approximation? There's two ways. I'll show you the hard way first. N factorial is approximately what, according to Stirling? Calculus, right? Okay, fine. Square root of 2 pi n, n over e to the n. Okay? That looks right. Do you believe me? We've seen this before, maybe, somewhere, Stirling approximation. It's okay, rabbit it out of a hat trick. We'll do it the easy way later. But first off, that's the approximation. So what we do say here is then we can just plug that into the log here, and we're going to get that it's greater than equal to log of, what is that? Square root of 2 pi n times n over e to the n, which is going to be equal to log of, and this is again log base 2 for now, log base 2 of square root of 2 pi n plus log of n to the n plus, and then we get that e to the minus n, so it's going to be a minus log of e to the n. Does that sound right? Log rules? This is approximately some constant c plus the square root of n. So what is that going to be? That's going to be less than log, though. So it's going to be O of log of n. Plus, we have O of log of n to the n. Plus, minus, I don't even, what is that? Minus O of n, something like that, right? So what is, we take the dominating term always. What is log of n to the n, approximately? Yeah. Log rules, n log n. So we see that log of n factorial is kind of approximately n log n. Yes?
Could you just break n factorial into n minus 1 and do log
Oh,
of n?
that's the easy way. We'll do that in a second. I wanted to show you the hard way, though. If you know Stirling's approximation, sometimes things can be quick. But if you don't know Stirling's approximation, you've got to do an underestimate, overestimate argument, which is what we'll do in a second. So this is the first argument. So we have sufficiently showed that the number of comparisons must exceed n log n. And therefore, if each comparison takes one step, which is what we assume, then the runtime is, as we say, theta of n log n. So in some sense, merge, sort, and so on are optimal. Questions on the Stirling's approximation? Let's do the easy way. Again, we want to compute a log of n factorial, let's say even base 2, right? So what we can say is that n factorial is equal to n times n minus 1 times 2 times 1, right? So let's underestimate, and sometimes underestimate, overestimate, it's a little bit of a skill. Let's underestimate it. So we're going to say n factorial is in fact less than or equal to, were we to do this product, n times n minus 1 to n over 2. So what we're going to do is basically just ignore these factors. But that's okay, that gives us an underestimate, right? Okay? Now we're going to underestimate again. This is an increasing product, but the least term that any of these could be is n over 2. So we can underestimate each product by that. And that's n factorial. So what is this? Yes. We have n over 2's, and we have n over 2 of them, right? So now we just kind of do a little bit of plug and chug. Log of n factorial is less than or equal to log of n over 2 to the n over 2, which is n over 2 log of n, and I'll put 2 to the negative 1, because I'm going to make a mistake if I don't, n over 2 log of n plus, minus log of 2, which is like approximately n log n minus n, which is equal to n log n. Done. Which one is simpler? This one, I think they're different. The difference goes in their own way. That one's a plug and chug if you knew trivia. This one takes a bit of massage, and you would have to kind of know how to take the half of the factors to the half power. This, if you didn't know how to do this, I think this is not as easy as it looks to come up with it, right? Questions on these two arguments? We've proven the number of comparisons in the comparison model explicitly. Any comparison-based sorting algorithm must take n log n steps. Now, the next question is just the final little detail. What about if you're not working in the comparison model? It depends. And if you're not explicitly relying upon comparisons and you're allowed to do other operations, then you can even have linear time sorting algorithms. One of my favorite is as follows. So it's going to be some sort. We're going to take on input an array. And what we're going to do is, let's call this an array 1 to n. We're going to say the processes are going to take on an empty array. And then we say for I is in 1 to n. What we're going to do is say add process pi, which is going to do the following. It's going to say time.sleep I seconds, and then it's going to print I. And then at the end, we add that to the process list, and then we run all processes at the same time. Okay, so how long does this take? Yeah, it takes the size of the max element. It's kind of a hack, because how long does it take to take the processes? The computer actually dovetails all this for us, right? So what happens is if you have an array of, let's say, 1, 2, 3, no, let's do like 17, and then 12, and then like 4. Each of these is going to spin, if you have n elements in your array, you're going to spin up n processes, and then you're going to do time.sleep each one, and then you're going to print the ith one. So if you wait 1 second, you'll see a 1. You wait 2 seconds, you'll see a 2. 3 seconds, nothing will happen. 4 seconds will take 4. 5 seconds will pass. 6 seconds will pass. 12 seconds will pass. 12 will print, and then 17 will print. So that actually doesn't take, the runtime of this algorithm and the number of seconds is actually the max element of the array. Is it linear time? You can do things like this with your actual programming. In the theory of algorithms is just too hard to analyze. We don't do this at all. This is not fair game for us. So, and in fact, it's not necessarily true that if you have several processes with time.sleep and your architecture does something fancy, it's not necessarily true that it's going to exactly take 4 seconds. Because it may pause one process to run the other. It's not a multi-core thing. And if it was a multi-core thing, you have a finite amount of cores. You don't have n cores. You can't do this for an array of size 1 million if you have an 8-core machine, right? So many such lower bounds are difficult. And it's not for reasons like this, but this kind of can help explain, like, there are many diverse things that program can do which don't fit nicely into any understanding of what we have for algorithms, right? Questions? All right.